So today we are going to talk about the electron arrangement of the atoms. The Bohr model of the atom was designed by Niels Bohr. The Bohr model places the protons and neutrons in the nucleus and electrons in energy levels around the nucleus. Before you can learn how to draw a Bohr model of an atom, you must learn a little bit about the periodic table of elements. Through experimentation, Niels Bohr was able to determine the maximum number of electrons in each energy level. So he said that there are 7 energy levels, 1, 2, 3, 4, 5, 6, 7. And through experimentation, he found that in the innermost energy level, the energy level that is closest to the nucleus, the maximum amount of electrons that first energy level could hold were 2 electrons. In the second energy level, the maximum number of electrons was 8. The third, 18. The fourth, 32. Fifth, 18. Sixth, 8. And seventh, 2. So you do need to memorize that order. 2, 8, 18, 32, 18, 8, and 2. It sort of makes a pattern. 32 is in the center, and then these two, the third and the fifth are 18, the second and the sixth are 8, and the first and the seventh are 2. So it kind of ascends 2, 8, 18, 32, and then it descends in the same reverse order, 18, 8, and 2. You do need to memorize that. Okay, take a look at this picture right here. This picture shows the first 36 elements, excluding the transition metals, and their atomic structure, how many rings they have and how many electrons they have. What is similar about all of the elements in each group? So the groups go vertically. So just take a look at any group right here, any elements in the same vertical column, and find something that is similar about those elements in the same column. Well, let's take a look here. There's one light purple ring. In that light purple ring, there is one electron in its outermost shell. In this element, it has 2 rings, a light ring and a darker purple ring. But in its outermost ring, notice that it only has 1 electron as well. If you take a look at the third one down, it has 3 rings, light purple, dark purple, and then sort of bluish. If you look at that outer bluish ring, there's only 1 electron in that outermost ring. If we look at the next one down, we have 4 rings, light purple, dark purple, blue, and then kind of darker blue. If you take a look at that outside dark purple ring, notice there's only 1 electron. If we go over here to column number 1, 2, 3, 4, 5, this is column 5, notice that in its outside ring, there's 1, 2, 3, 4, 5 electrons. In this guy's outermost ring, 1, 2, 3, 4, 5. In this guy's outermost ring, 1, 2, 3, 4, 5. Let's take a look at this guy. This guy is in column number 7. In its outer last exposed ring, it has 1, 2, 3, 4, 5, 6, 7. This guy, 1, 2, 3, 4, 5, 6, 7. And this guy, 1, 2, 3, 4, 5, 6, 7. Now, in row or column 8, the only kind of weird thing is that this element right here has 2 electrons in its outer ring, whereas everything else, if it follows the pattern, should have 8, like 1, 2, 3, 4, 5, 6, 7, 8. So we'll talk about those noble gases in that 8th column separately. But what you should have noticed, and as I pointed out, is that elements that are in the same group, the same vertical column, all have the same number of electrons in their outermost energy level or shell. So whether their outermost energy level is the first shell, the second shell, the third shell, fourth shell, the last energy level that is exposed to the outside world always has the same number of electrons as the element on top of it or below it. We call these outermost electrons valence electrons. That is a term we will be using over and over for the rest of the year. Valence electrons are very important in chemistry because they are the electrons that are involved in reacting. They are the only ones that can be lost, gained, or shared. You cannot lose, gain, or share inner electrons. So the valence electrons are able to help us predict what elements will combine and what elements will react. They tell us how the atom is going to react with other atoms. So the vertical columns are called groups. Elements in similar groups share similar properties, specifically how they will react with other atoms. They share the same number of valence electrons. A valence electron is an electron in the outer energy level of an atom. You can easily calculate the number of valence electrons by counting the group it is in. We exclude the transition metals. They follow their own rule. They don't follow this nice pattern. But all elements, we're going to call this group 1, will have 1 valence electron. In group 2, all the elements in that group will have 2 valence electrons. Again, we're going to skip over the transition metals. All the elements in group 3 will have 3. All the elements in group 4 will have 4. All the elements in group 5 will have 5, 6, 7, and 8. The only exception to group 8 is helium. The reason that helium does not have 8 valence electrons is that its atomic number is 2. So it does not have 8 valence electrons. So it can't have that 8. It just has 2, which is full for the first ring. You can figure out the valence electrons by looking at the group number the element is located in. So I just did that for you. So for example, gallium. Gallium is right here. How many valence electrons does it have? The correct answer is 3, because it's in the third group. Strontium. Strontium is here. How many valence electrons would strontium have? 2. Xenon. Xenon is here. It has 8 valence electrons. Rubidium, right here. It has 1 valence electron. Arsenic, As, has 5 valence electrons. Hydrogen has how many valence electrons? 1. Astatine. How many valence electrons does it have? 7. Now, that is the pattern down a vertical column or group on the periodic table. Let's take a look at the pattern across a row or a period on the periodic table. What do you notice that is common about all the elements in the same period or row? You should see that they all have the same number of energy levels. So in group 1, these two, I'm sorry, not group, in period 1, each element, there's only 2, has 1 energy level, that light purple ring. If you take a look at the elements in period 2, or row 2, they all have 2 energy levels, the light purple and the dark purple. Now, their valence electrons change. This one has 1, this one has 2, this one has 3, this one has 4, 5, 6, 7, 8. So that changes, but the number of energy levels is the same across a period. Here, they all have 3. Here, they all have 4. So we can count the periods or rows down. 1, 2, 3, 4, 5, 6, 7. Don't forget the lanthanide, the one that starts with La, and the actinide series. They are part of row 6 and row 7. They just get pulled out because they would make the periodic table way too wide in a standard textbook. Horizontal rows are called periods. Elements in similar periods share similar number of energy levels. This is where the electrons hang out. So, for example, boron, which is in period 2, would have a nucleus and then 2 energy levels. This 2 and this 8, those are not really the number of electrons that boron has. Those are just to remind you that the maximum number of electrons the first ring can hold is 2, and the second ring is 8. But boron does not have an arrangement of 2, 8 because boron's atomic number is 5, so it only has 5 electrons, and we'll talk about how to put those in properly in a couple minutes. But these numbers that appear are just to remind you the maximum number of electrons each energy level can hold. Chlorine. Chlorine is in period 3, so it has a nucleus and then 3 rings. Gallium, period 4, so it has a nucleus and 4 energy levels. Lithium has 2. How many does tellurium have? 5. How many energy levels does neon have? 2. Okay, periods and families. Periods 1 through 7 run across the periodic table. So the periods run across horizontally. All elements of a period have the same number of energy levels. Groups, also known as families, run down the periodic table. So the groups run vertically. Members of a group, with the exception of helium, have the same number of electrons in their outside energy level. These electrons are called valence electrons. Iodine, for example, would have 5 energy levels, and it would have 7 valence electrons. So the period tells you the number of energy levels, and then the group, this way, tells you the number of valence electrons. Fill in the table with energy levels and valence electrons. You can press pause to give yourself a second to test it on your own. Calcium has 4 energy levels, 2 valence electrons. Fluorine, 2 energy levels, 7 valence electrons. Aluminum, 3 energy levels, 3 valence electrons. Potassium, 4 energy levels, 1 valence electron. Carbon has 2 energy levels and 4 valence electrons. Phosphorus has 3 energy levels and 5 valence electrons. Radon has 6 energy levels and 8 valence electrons. And hydrogen has 1 energy level and 1 valence electron. So now that you know how an element's position on the periodic table affects, or how an element's position on the periodic table can tell you the number of energy levels and valence electrons, we are now ready to learn how to draw the Bohr models of these atoms. So in step 1, what a Bohr model shows is the nucleus of an atom, the energy levels of the atom, and where each electron is placed in those energy levels. So you draw a circle to represent the nucleus in step 1. The inside of it, you're going to write how many protons and neutrons there are in a strontium atom. We're going to do strontium, for example. The strontium has an atomic number of 38. Its atomic mass is 87.62. So it has 38 protons, and then its number of neutrons is, we're going to round 87 to the number 88. We're going to subtract 38 from it, and we should get this. I remember being wrong in previous years. It should be 50 neutrons. So you're going to draw a circle with 38 P positives and 40 N zeros. Step 2, you're going to draw the number of energy levels of that atom based on its period number. Draw only a section of the circle to represent the energy level. So strontium is in period 5. So you are going to draw 5 circles, or you can just draw semicircles to represent the portion of the full circle that represents the number of energy levels of strontium. Again, the number 5 comes from period 5 that strontium is in. Step 3. Fill the last energy level, the outside valence shell, with the correct number of electrons based on its group number. You always do the last energy level first. So strontium is in group 2. So you fill in the last energy level first. Step 4, go to the first energy level and fill it with the maximum number of electrons. Do this with the other energy levels until you get to the second to last energy level, keeping in mind the 2, 8, 18, 32, 18, 8, and 2 max rule. So here, you're going to fill in your 2, 18, 8, 18, and then leave the second to last energy level empty for just a second so that you can calculate how many should go in there. The reason you have to pause on that energy level is that it's not necessarily going to be filled to its maximum. The maximum that the fourth shell can hold is 32, but you are not going to have all 32 electrons there, because then that would exceed the number of electrons that strontium has, which is 38. So you have to do a little calculation. For step 5, to get that number, you add up the number of electrons you have and subtract it from the total number of electrons in a strontium atom, which is its atomic number. That number gets placed in that second to last energy level. So because we have 2, 8, 18, 32, that is a total of 30 electrons, I need 38 electrons. So if I subtract those two, I see that the last 8 electrons will go in that second to last energy level. So my configuration for electrons is 2, 8, 18, 8, and 2. Let's go ahead and draw aluminum. So I will draw my nucleus here. The aluminum has an atomic number of 13, so I'm going to draw 13 protons there. I don't have a periodic table in front of me, so I cannot tell you what its mass is, but I know that it has 14 neutrons based on the fact that I just peeked on that previous page, so it must have an atomic mass of 27. So that's where the 14 comes from. Now, if you look at aluminum, it is in period number 3. So you're going to draw 3 energy levels there. It is also in group number 3. So you fill in the 3 electrons out there first. Then you fill in your center or your inner ring first and put 2. So 2 plus 3 is 5. You have 13 electrons you need filled. 13 minus 5 gives you 8. So the configuration is 2, 8, 3. That's a better picture. Bromine. So bromine has 35 protons, its atomic number. And I'm going to cheat because I, again, don't have a periodic table in front of me right where I am. We're going to put in 45 neutrons, which is its atomic mass minus its atomic number. Bromine is in group number 5. So we're going to, or no, not group, period 5. 1, 2, 3, 4, 5. Its group number is 7. So the 7 goes in first. The rest of them get filled in. 2, 8, 18. I add them up. 2, 8, 18, and 7. That gives me 2 plus 8 is 10. Plus 18 is 28. Plus 7, shoot, my bad. This is what happens when you do this without a periodic table in front of you. Bromine actually only has 4 rings because bromine is in period 4. So its configuration is 2, 8, 18, and 7. All right, let's do magnesium. I'm going to pause this for a second and go grab myself a periodic table so I don't make that mistake again. Okay, so I'm literally doing these notes at like 11:30 at night, so I don't have my normal periodic table references like I do at school. Let's go ahead and do magnesium. So magnesium, we're going to draw our nucleus, and its atomic number is 12, so I'm going to put 12 protons here. Its atomic mass is 24.3050, depending on what periodic table you might have different decimals, but it's approximately 24. So 24 minus 12 gives me 12 neutrons. So put 12 neutrons there. Next step, the number of energy levels. Magnesium is in period 3, so it's going to have 3 shells. Now we can fill in our electrons. The valence electrons go in first. It's in group 2, so it gets 2 electrons out here. Then we start from the inside out. We have 2 electrons there. 2 plus 2 gives me 4 electrons that I have. I need 12 though. So 12 minus 4 gives me 8. Those 8 go right there. So the Bohr model for magnesium looks like this. Let's take a look at fluorine. Fluorine, draw our nucleus. Fluorine has an atomic number of 9, so it has 9 protons. Its atomic mass is 18.9984, so it's approximately 19. 19 minus 9 gives me 10, and that 10 will go here for the number of neutrons. Next, energy levels. Fluorine is in period 2, row 2, so it gets 2 rings. It is in group 7, vertical column 7, so I fill in those 7 first, and then put the 2 here. These should add up to the atomic number of 9, which it does. So the Bohr model, atomic model, looks like this. Let's try selenium. Selenium is element 34, 34 protons. Its mass is 78.9, so approximately 79 minus 34. That is 545, so it is 45 neutrons. Selenium is in row or period 4, so I'm going to have 4 shells. It is in group 6, so this comes from, again, the group number that it's in. Then you start from the inside out. 2 electrons, 8 electrons here. These are, again, come from the maximum number of electrons each of the energy levels can hold. So 2 plus 8 is 10, plus 6 is 16 electrons, and I need 34. So 34 minus 16 4, 5, 6, 8, 2, 18. So those 18 get filled in here. When you add up 2, 8, 18, and 6, they should add up to selenium's atomic number of 34, which they do. And that is where we will end today.